Hey y'all, this is the first of two videos on scaling. In this video, we're just going to introduce the topic in general, and then in the next video, we will do a couple of practice problems with it. Make sure you are filling out the forms as you go. So I'll start with a little science fiction example. All right, let's say that we have Alice here, and Alice gets hit with a shrink ray. Basically takes Alice from whatever her original height was and drops her down to be 1/2 her original height. She gets scaled down. Okay. Now, I'm going to give you some stats about Alice as she was as a regular human adult. Alice was 68 inches tall, right? So 5'8". 7-inch wrist circumference. Her jeans used about 14 square feet of fabric. The volume of her brain was 1,400 cubic centimeters. She weighed 150 pounds, and she could bench press 75 pounds, about half her weight. So I want to go through and figure out what Alice looks like now that she's been shrunk down to half her height. Obviously, her height will go from 68 inches to 34 inches. Her wrist circumference, that is the distance around her wrist, will go from 7 inches to 3.5 inches, right? So those are basically just lines on Alice's body, right? If I were to go measure from the top of her head to her feet, right, that's a straight line. That's her height, that gets shrunk in half. And her wrist circumference is just a line I draw around her wrist. Right? That also gets shrunk in half. What about the fabric used in her jeans, though? Right? That was 14 square feet. We might initially suspect that when that gets scaled down, that ends up being 7 square feet. But notice that this is the first measurement that we're looking at that is in 2 dimensions, right? Height is one-dimensional because it's just measuring a straight line from your feet to your top of your head, as is wrist circumference. Even though it's kind of going around, right, it is just a straight line measurement, right? Remember thinking about TV as, for instance, how much aluminum foil could I cover this thing with, right? That's not really a relevant question for height or wrist circumference because it's just one straight line. But imagine how much aluminum foil would I need to cover her jeans. That's a weird example, but that's what I think of when I think of 2D. Right? So what happens to her jean fabric? Okay. Let's toggle over to a different 2D example. Right? Let's take this square. You might imagine that Alice has a tattoo of a square on her hand. I want to know what happens to that when she gets shrunk down. Okay. Originally, that was a 2x2 square tattoo, and it has area 4 square inches. When she gets hit with the shrink ray, right, these lines, right, get halved in length, right? So that is now a 1 inch by 1 inch square. Notice that the area of this square is 1 by 1 square inch. So notice that although the sides each were halved, right, from 2 to 1 and 2 to 1, the area was not halved, right? It went from 4 to 1, right? It was multiplied by 1/4, right? So the area actually got multiplied by that 1/2 squared, right? So we go from the area before to the area now. We multiplied by this scaling factor, which we'll define in a second, squared. Right? So for her jeans, if we want to figure out how much fabric her jeans take up now that she's shrunk, that's a 2-dimensional thing we're talking about, right? It's the jeans that's covering her legs. Right? So 14 times 1/2 squared is 3.5 square feet. Right? Because we are dealing with area, which is a 2-dimensional measure, we actually have to multiply by 1/2 not once, but twice, right? What about the volume of her brain, right? Volume is, of course, a 3-dimensional measure, right? We can go through the same process, right? Imagine that we're shrinking down a cube that looks like this. It's 2 by 2 by 2. That has a volume of 8 cubic inches. But if that gets hit by the shrink ray, All of these one-dimensional lines, right, are shrunk down to 1 inch, 1 inch, 1 inch, and now the volume is 1 cubic inch, 1 times 1 times 1. Okay? So when we went from a three-dimensional object and scaled it down by a factor of 1/2, right, we actually had to multiply that scaling factor, that 1/2, 3 times. 1/2 times 1/2 times 1/2, right? So 1/2 cubed. So notice that what we're doing here is we are multiplying by this scaling factor, this thing that is affecting only the one-dimensional lengths, raised to the dimension that we're interested in here, right? So 1/2 to the third, 1/8. So if I want to get her the volume of her brain, that's going to be her original volume of her brain multiplied by the scaling factor raised to the third power, okay? What about her weight, right? Take a second. I want you to give me your intuitions about what her weight would be after she is hit with this shrink ray. So put your thoughts on the form. Remember, I don't know is always an okay answer. Right? Weight is going to be most closely connected with volume, right? Excuse me, if I'm talking about weight, right, let's think about, is that a 1D, a 2D, or a 3D measurement about Alice? Right? It's going to be more of a 3D measurement, right? I'm measuring kind of everything that is Alice, including everything that's inside Alice, right? Her organs and all that, right? So weight is very much still a three-dimensional measure. So we're actually going to multiply by that scaling factor raised to the third power because we are talking about a 3D scale down, right? So instead of just multiplying 150 by 1/2, we'll multiply it by 1/2 3 times because we are dealing with a three-dimensional change. Okay, and then the last one I want to look at about Alice is how much she can bench press. Right? I'm not going to ask you all to give me your thoughts on this because it's a little bit counterintuitive. It turns out that the way that we actually measure someone's strength, right, just from an anatomical standpoint, is if we take a cross section of their arm, we're basically going to measure the number of muscle fibers that can kind of fit in that area. Right? So we're actually just looking at a two-dimensional cross-section of her arm. So her strength, weirdly enough, is actually going to be measured in a two-dimensional manner, right? Which means that if we're trying to get her new bench press ability, right, we want to take her original amount she could bench press and then multiply it by 1/2 squared because we just saw that her strength is a function of the cross-section of her arm, right? And that's going to be a two-dimensional measurement. Okay? So she could only bench press 18.75 pounds. Let's talk about how walking around feels for Alice. Sorry, I was like, why is this? Okay. So her legs, right, are going to be 1/2 squared as strong as they were, right? Think about her leg strength, right, as what she's walking around using, right? Well, her leg strength is going to be reduced by the same amount that her arm strengths were, right? So it's going to be 1/4 as strong as it used to be, right? But her weight, right, what she's trying to hold with her legs, is 1/8 what it used to be, right? We took her weight and multiplied it by 1/2 cubed because weight was a three-dimensional measure. So although she is only 1/4 as strong, she's only 1/8 as heavy. So walking around is actually going to feel a lot better for Alice than it used to. What if Alice instead grew by a scaling factor of 10? What if we took that shrink ray and reconfigured the settings and then took Alice again starting at regular height, right? And she grew by a factor of 10 instead of shrinking by a factor of 1/2. I want you to try to figure out what would be the effects on Alice's size, her strength, her weight, and her ability to walk. We're scaling her up now, but the idea is going to be exactly the same. You want to figure out what dimension we are trying to scale up, 1D, 2D, 3D, right? And then figure out how to modify her original attributes. You'll have to go back a few slides to find those again, right? But tell me what happens to her on the form, right? In terms of her size, her strength, her weight, and her ability to walk. So as far as her height would go, remember height is a one-dimensional measure, right? So she is strictly this scaling factor of 10 means that she is just going to be all things that are one-dimensional about her will be 10 times the size they used to be, right? So her height, which again is one-dimensional, is just going to be multiplied by a factor of 10. She'll now be 680 inches tall. In terms of her strength, right? Remember that we measure that as a two-dimensional property. So we're going to take 75 times the scaling factor squared because this is a 2D property. So she will actually be able to bench press. Actually, I need to modify this. Right? So this is 7,500 pounds, right? Adding on the 2 zeros after the 75. But she also now weighs 150,000 pounds, right? So make sure that math is right. 1, 2, 3, yep, right? So that's about as much as all the cars in Founders parking lot, right? So to answer the fourth question about her ability to walk, walking is going to be a really huge pain, right? So she is, although she is 100 times stronger than she used to be, right? Both in her arms and her legs, she's going to weigh 1,000 times as much as she used to weigh, right? So she's gotten a lot stronger, but a lot heavier, right? So this is not going to be a good time for Alice. Okay. So there is actually some evidence for this kind of shrinking and growing phenomenon in terms of strength in weightlifting, right? So on this little table, I have a bunch of different weight classes for different lifters. And then we have their record for how much they could lift, right? What I want to pay attention to, though, is actually how much they can lift as a fraction of their body, right? So imagine, this is going to be kind of bizarre, imagine that instead of lifting weights, I'm going to see how many of, I get a cloning machine. I want to see how many of me can I hold up, right? If I'm in the 56 kilogram weight class and I can lift 138 kilograms, how many of me can I lift, right? I can lift 2.46 of me, right? So about 2.5 of me, right? But the heavier I go, right, the less me's I can lift, right? And that seems kind of bizarre, but imagine if we're walking around, right? That's basically all we're doing. We are lifting us, right? And what we just found is that the larger you are, the more you are scaled up, the harder it is for you to walk around. And to a small extent, we see that with these weightlifters. The heavier ones, right, the ones you can think of as being scaled up, right, are able to lift less of their own body weight, right? If you were to try, they were trying to lift themselves, this 105 kilogram person could generally only lift less than 2 of themselves, whereas the 56 kilogram person could lift almost 2.5 of themselves, right? So these lighter people, the ones who are scaled down and smaller, are able to bench press more relative to their own body, okay? So these problems in which we are scaling an object up or down by some factor are called scaling problems, right? We're going to talk about why these can be useful in just a second as our little wrap up here. Right? But I want you to see if you can think of an example on your own, right? For some kind of real world problem, as in not involving this fictitious shrink ray, right? Where this kind of problem might be relevant. So take a second, see if you can think of one and record it on the form. All right, so these problems primarily come up in if we are doing any kind of modeling, right? So for instance, right, modeling is not just what scientists do when they are trying to make a model of some greater system. In something as simple as a map, right, is a model for some larger land area, right? When you have a map, it's going to give you the general kind of a miniature of the area you're looking at, right? And it will have a little key at the top right saying 1 inch equals, I don't know, let's say 200 meters or something, right? That is your scaling factor, right? It tells you how much, how much you are basically scaling up by when you are trying to transcribe from the map to the real world, right? And on your, the way this will be useful, what we just covered is on your homework, it might be straightforward to see, okay, if I have a path that's 2 inches on the map, how long is that on the in the real world? But what if I ask you, okay, I have a lake, right? And I tell you how big the lake is on the map. How big is that in the real world, right? Lake would be two-dimensional, right? I'm talking about the surface area of the lake. So these kind of strategies are going to be useful for that. Okay? Same thing with architecture, right? When you are an architect, you don't want to just immediately start building a house. You usually want to have some kind of blueprint, oftentimes a 3D blueprint for what it's going to look like, right? A little model of it, right? And so you'll want to know how to scale the intended house down or scale the model up to look like what you're going to build. Right? And any kind of product design. Oftentimes, if you are designing something, especially something very large, you might want a smaller model of it first. Also, the estimations that we talked about on Monday, right? There are certain questions that you might be asked where knowing how to scale something might be useful. We'll work through a problem in just a second where we try to estimate how big most cucumbers are, right? Without actually having to measure or weigh a cucumber. Okay, and let's see, I think that's the end of this video. Make sure you're filling out the form, and I'll see you in the next one.